Hello, everyone. It is 5:30 p.m., Wednesday, July 15th, and it's time to get our class started. When we last spoke, we were working on chapter 10. I'd went up through, I think, example 10.9, and today we're going to try to knock out the rest of chapter 10, starting with example 10.10, and maybe even jump into chapter 11 a little bit. I don't really want to overburden you or whatever, but anyways, that's what we're going to go for. So let me start by sharing my iPad screen. I want to remind everybody, you guys have a online or a face-to-face test, quote unquote face-to-face test that's been done by Respondus Lockdown Browser and Respondus Monitor with the normal rules. Remember, if you don't show me your work on the problems that require work, you would get no more than maybe one third of the credit for each problem, even if you have the right answer. So that's a maximum one third of the credit for a given problem if you have the right answer but no work. But again, that's the maximum. And you're supposed to show me your work. You're supposed to show it neatly. I recommend that you write down your equation as it's seen on the equation sheet. And then from that pure form, substitute the numbers or solve it algebraically and then substitute the numbers with the units, that sort of thing. That allows me to give you a lot of partial credit if you don't get it right, that sort of thing. And remember to follow the instructions during the Respondus monitor session where they tell you to, for instance, scan the work area and then show me the front and back of all the pages that you have laid out on your desktop where you plan on working on the test. And then at the end, you're supposed to submit photos of each of your work for each of your problems. Try to do that as neatly as possible. If you're moving when you hit the button, then obviously the thing's going to come out blurry and that could be a problem. And then you're supposed to email me those worked problems in a single PDF file, photographs of each of the problems neatly done so that I can read them. And they're supposed to be sent to me within 20 minutes of submitting your test. So make sure you get that done as well. All missing any of that is really grounds for you to get a zero. And at best case scenarios, I make you retake it. Worst case scenarios, you get a zero and it stays a zero. So please work on that. Let me go ahead and share my iPad screen with you guys so we can get started. So this should come up in a second, and I am referring to the problems in the textbook. So as always, if you have your ebook open, that would be best case scenario for you so that you can follow them. But example 10.10, a heavy pulley. It says specifically a 15 Newton force is applied to a cord wrapped around a pulley of mass M equals 4.00 kilograms and radius R0 equals 33.0 centimeters. The pulley accelerates uniformly from rest to an angular speed of 30.0 radians per second in 3.00 seconds. Assume there is a frictional torque tau excuse me, tau sub friction is equal to 1.10 Newton meters at the axle. Determine the moment of inertia of the pulley rotating about its center. Okay, so I've written down all the information here already. And the information we have, of course, is the tension, the 15 newtons, the mass of the pulley, which is 4.00 kilograms, the radius, which is 33.0 centimeters. Obviously, we're going to have to use that in meters. And I went ahead and left what I wrote down as the solution, even though I normally normally don't write that till after the problem starts, but that's okay. The time required for it to reach that new angular velocity is 3.00 seconds. And like I said, the torque due to friction is 1.10 Newton meters, and we're asked to solve for I. The equations we're using are the summation of the torques is equal to I times alpha. Remember that works in any frame as long as the axis of rotation doesn't change and the reference frame is inertial. So, in other words, if it obeys Newton's first law of motion or Galileo's law of inertia, or if it appears to, then it should be an inertial reference frame, and therefore you can use that. If not, then you have to use that other version, which is the same equation, but we actually have to calculate it for the center of mass. So the summation of the torques about the center of mass, the moment of inertia about the center of mass, and the angular acceleration about the center of mass. So first off, we're going to start off by calculating the average alpha, which we're going to assume is in fact a constant. And in fact, I might need to make that a little smaller there. So the average acceleration, which we said we expect is going to be a constant, is alpha bar is equal to omega minus omega 0 over delta t. And the omega, of course, is 30.0 radians per second minus 0 radians per second divided by 3.00 seconds. And even I can do that math. That's 10.0 radians per second. Again, that's the way you should say it, even though you can write it as radians per second squared, because it literally means that the angular velocity is going to change by 10 radians per second each second. Now that I have that, I just need to work on the left-hand side of the equivalent of Newton's second law, the summation of the torques. And the summation of the torques should be equal to, in this case, I am going to assume that the tension going or the tension going downward is causing a rotation that's in the counterclockwise direction, and I'm going to call that the positive torque, and then the other torque will be a negative. And torque, of course, is equal to, there's a lot of different versions of it, but we could say the magnitude is equal to R perpendicular times F, R F perpendicular times R, or you could say F R sine theta, or you could say the cross product. In this case, we actually have the lever arm, which I've taken the time to draw for that force F, and you see that it's perpendicular. As you can see from this description right here, I've shown you that that's 90 degrees. So all we have to do really is multiply the radius times the force. And in this case, the radius times the force, or the force times the radius, is going to be 15.0 newtons times 0.330 meters. And then the other one is going to be minus 1.10 Newton meters, because that's its torque due to friction. And the 15 times 33.0, or 0.330, gives me 4.95 Newton meters minus 1.10 Newton meters, which is equal to 3.85 Newton meters. That's the left-hand side. So now if we go ahead and apply Newton's second law for rotation, we get the summation of the torques is equal to I times alpha. And in this case, that's going to be 3.85 Newton meters is equal to I times alpha. And we already figured out that alpha is 10.0 radians per second. So we can say that I, the moment of inertia, is equal to 3.85 Newton meters divided by 10.0 radians per second. Remember, a radian is a pure number, really, so you don't have to excuse me. So you don't really have to have anything to cancel out to erase it. You can just drop it at any point, and you can also, of course, add it at any point. But the Newton meter becomes, we get the number, by the way, 3.85 divided by 10 is 0.385, but I want to show you what's going on with the units. So the Newton meter is a kilogram meter per second squared is the Newton, and then a Newton meter is a kilogram meter squared per second squared, and then we're dividing that by a radian, which again is a pure number, so we can drop that at will. And you see that this second squared down here is going to cancel out with that second squared up there, because when you divide by a fraction, you multiply by its reciprocal. That reciprocal will be second squared over radians, and you're left with just kilograms meters squared, and that's the actual units that we expect for the moment of inertia. So the moment of inertia is 0.385 kilograms meters squared, like that, and that's our answer. Normally I'd ask if there were any questions, but there's no one here today, so we're going to just press on. Oh, somebody just came in, so yay for that. All right, now we'll move on to the next example, and this is example 10-11 or 10.11, and it says pulley and bucket. I'm sorry, I keep yawning, but pulley and bucket. Consider again the pulley in example 1010, but instead of a constant 15.0 Newton force being exerted on the cord, we now have a bucket of weight, W equals 15.0 newtons, and that of course implies that the mass is 1.53 kilograms, and that bucket is hanging from the cord. See the figure below. We assume the cord has negligible mass and does not stretch or slip on the pulley. Calculate the angular acceleration A of the pulley and the linear acceleration A of the bucket. Angular acceleration should have been alpha, but the book has a typo there. It says calculate the angular acceleration A, but they really mean calculate the angular acceleration alpha of the pulley and the linear acceleration A of the bucket. Assume the same frictional torque, 1.10 Newton meter, acts on the pulley. Now, with this, since we're told to assume the cord has negligible mass and does not stretch or slip, that covers a couple different things. As the pulley spins this way, allowing more and more rope to go down, more and more rope goes down, so you actually get a bigger and bigger mass. The weight of 15 newtons is hanging on it, but as more rope doles out, that gets a heavier and heavier mass. But that heavier and heavier mass we're assuming is negligible, so we can skip that part. So that's one of the things that it being negligible mass tells us, that we don't have to allow for the additional rope to come in and weigh more. The other thing is that it doesn't stretch or slip. The fact that it doesn't stretch or slip means that we can use equations like S equals R times theta, meaning if a certain amount of string comes out of the pulley, let's say S, then that amount of string will be exactly equal to the radius of the pulley times the angle through which the pulley rotates. That's what it means to not slip or stretch. Additionally, you can take the derivative of that, and that means if the pulley moves down or allows the rope to move down 1 inch in 1 second, then the a point on the circumference of the pulley is going to move a arc distance of 1 inch, and that, of course, divided by 1 second would give you the velocity of the pulley as well, the tangential velocity. Okay, so the V equals R times omega works as well, and you could do the same thing for the A equals R times alpha. So that's what all this sliding without slipping, stretching, not stretching, that sort of stuff, that's what that's going to do. It just tells us that we can use that series of equations, S equals R times theta, V equals R omega, and A equals R times alpha. So now we begin. The solution is going to require us to apply some equations. So I normally use this to just write down the equations that we're going to need. And the equations we're going to need are, of course, Newton's second law, the summation of the torques equals I times alpha. Putting a coordinate system attached to the space and sitting over top of this pulley is not going to make a non-inertial reference frame, so we don't have to worry about it having to be through the center of mass, even though in this case we are actually doing it through the center of mass for the pulley anyways. Okay, we're going to need that, but we're also going to need the summation forces equals mass times acceleration, which is Newton's second law, because it turns out we're going to have to have, and that's 1.53 kilograms. We're going to have a free body diagram, which I've already drawn for the Y motion of the actual bucket hanging. So now all we have to do is go about calculating the summation of the torques, and we saw last time exactly what the summation of the torques would be. So the summation of the torques is going to be 15. Oops, excuse me. I almost did the same thing I did last time. We have to sort of reconsider this pulley as a free body diagram for rotation. And to do that, let me do this. I'm going to try to draw it fairly neatly. So I'm going to use the tools that my program allows me and draw that really neatly. And what we're going to see at this point is that, in fact, there's going to be a tension pulling this way, and that tension is T. And notice it leaves tangential to the circle, so that the lever arm vector, which would be this, is automatically perpendicular to it. So we get a very straightforward formula. But we also have the other torque going this way, which is 1.10 Newton meters. So that's our free body diagram here. And I should also say that in this case, the free body diagram for the Y motion or for the linear motion is the 1.53 kilogram bucket hanging with a weight of 15.0 newtons due to gravity pulling it down and a tension slowing it down so that it doesn't fall at 9.8 meters per second per second. So now I can go ahead and write out what the Newton, or excuse me, what the left-hand side of Newton's second law for rotation is. That's the summation of the torques. Again, I'm treating counterclockwise rotation or counterclockwise causing torque to be a positive. So in this case, I'm going to say T times R, which is 0.33. So I'm going to say T times 0.330 meters minus 1.10 Newton meters is equal to, well, actually, that's it. That's all we can write right now for the left-hand side. Now, the whole equation is the summation of the torques is equal to I times alpha. So now we can say T times 0.330 meters minus 1.10 Newton meters is equal to I, which we found out was 0.385 kilograms meters squared. And then all of that is times alpha, which is one of the quantities we're trying to solve for. I'm going to go ahead and call that equation 1. Now I've got to do the summation of the forces in the y direction equals mass times acceleration in the y direction for the bucket. And in this case, we see that we have a 15 Newton force pointing down. Notice that that 15 Newton force pointing down is the direction that the bucket has to go to cause a positive rotation. Because I decided to say counterclockwise was positive. I want those two to both agree what's positive, because if I didn't, I'd have to have some weird equation like instead of V equals R omega, I'd have to have something like V equals negative R omega, or instead of A equals R times alpha, I'd have to have A equals negative R times alpha. So that's what I try to do to link those two up to just make sure that the positive direction corresponds with both of the diagrams, or in some cases, it might be three different diagrams. So with that being said, I see that the force acting in the positive direction is 15.0 newtons, and then the force acting in the negative direction is T, and then that's all equal to 1.53 kilograms times A, and we'll call that equation 2. Now, what I can do is I can solve equation 2 for T and plug that into 1. So solve 2 for T and plug into equation 1. So that's what we're going to do. We're going to say, for starters, equation 2 is going to give us the following, specifically 15.0 newtons minus 1.53 kilograms times A is actually equal to the tension, so I'll call that 2 prime because it was from 2. And now I'm going to plug that into 1 to get 15 point, actually, let me write it further to the left so I have plenty of room. 15.0 newtons minus, oops, I don't even need a parenthesis around there. 15.0 newtons minus 1.53 kilograms times A. All of that is the T, and that's replacing the T in equation 1. So next to that, I have 0.330 meters, and then minus 1.10 Newton meters is equal to the right-hand side, which is 0.385 kilograms meters squared times alpha. So the problem is right now it appears we have, in fact, an alpha and an A. But now we can go ahead and use the idea that A is equal to R times alpha as another equation. But again, that only applies because the rope is not slipping and the rope is not stretching. Because of that, we know that the A's and the alphas link up through the radius R. That being said, that's going to allow me to get rid of either the A or the alpha, and I'm going to choose to get rid of the let's choose to get rid of the A. I'm going to say the A is going to be replaced by R times alpha. So in that case, I now have 15.0 newtons. And really, I said I'm going to do this, but it really doesn't matter which one you chose. You could do it either way, and it's still going to work out right. Now I'm going to take, instead of A, I'm going to put in R times alpha. So this is going to be replaced with R times alpha, which is 0.330 meters times alpha, like that. So when I multiply 1.53 times 0.330, that gives me 0.5049, which is one extra sig fig. So I'm now going to have 0. Oops, let me keep writing it in purple. 0.5049. And now we see that the units, of course, are kilograms times meters, because I had a kilogram there already, and now I've multiplied it by a radius. That gave me a meter. And then all of that is still left to be times A, and then all of that's multiplied by 0.330 meters, and then minus 1.10 Newton meters is equal to 0.385 kilograms meters squared times alpha. Now I'm going to go ahead and distribute that 0.330 to both of the terms. We know that when I multiplied 15.0 times 0.330, we got 4.95. So this is going to be 4.95, and that's Newton meters. That's for the 0.33 times 15. And now I'm going to take the 0.33 times 0.059, and that's going to give me minus 0.1667, and that's kilograms meters squared. And oops, that was not supposed to be an A there. Notice I said I'm going to replace the A with R times alpha, but I left it as an A here. So let me fix that real quick. That is an alpha. And now because of that, we see that this number is 0.1667 kilogram meter squared times alpha. And that's what we expect, because the units on the left are Newton meters and the units on the right are kilogram meter squared times alpha. So this is the only way that would work, is if these units came out that way. So that works out pretty well. And then we're going to say minus 1.10 Newton meters, and all that's equal to 0.385 kilograms meters squared. And again, you see the times alpha. So what we're going to do now is we're going to pull the alphas over to the right hand side, and then the left hand side is going to become 3.85 Newton meters, which, remember, that's the same thing we got for the left hand side on the previous problem. But on the right hand side, it's going to be 0.385 plus point 1.667 with one extra digit there, and that's going to give me 0.5517, and that's kilograms times meter squared times alpha, like that. And from that, we can say that alpha is equal to 3.85 Newton meters divided by 0.5517 kilograms meter squared. And if you remember correctly, the Newton meter was a kilogram meter squared per second squared. So when I divide by kilogram meter squared, I'm just getting reciprocal seconds squared. And as always, we can just throw a radian up there and it'll be radians per second per second. So I'm going to take the 0.385 and I'm going to divide it by that 0.5517. And with that, I get 0.69, and we only had really 3 sig figs, so I'm going to call this 698. It's actually 6978, like that. And that unit is radians per second, like that. And that's our alpha. So I've now calculated alpha, and by calculating alpha, we can easily calculate A, and we're using A equals R times alpha, which I never numbered, but that's okay. So A is equal to R times alpha again, which is only true because the rope is not moving or stretching or sliding on the pulley. So in this case, I'm going to say 0.330 meters times times 0.6978, 0.6978 with one extra digit. And if I multiply that times 0.33, then I get 0.230, and that unit is meters per second every second, or meters per second, and that's equal to A. So now we have computed the linear acceleration. That's the rate at which the object is falling, which is clearly way less than 9.8. And you see that we get a markedly different acceleration. We get 0.6978, whereas the last problem we did, the acceleration was in fact 10 radians per second. And I use the same I, and I use quote unquote the same weight, only on the first problem, the one that we're looking at right now. I pulled down on that with a constant force of 15 newtons. But on this one, it's a weight of 15 newtons that's falling. If the force was a constant 15 newtons, then the bucket wouldn't fall at all. It'd sit perfectly still. That's not what's happening here. The bucket is actually falling. So it's not a full 15 Newton force that's acting on it. It's something less than that because it's actually accelerating, obviously not at 9.8, but it's accelerating at something less than 9.8. And that's why the acceleration is markedly less than 10 radians per second, as we had in the previous problem. Anybody have any questions on that? Uh, I'm trying to. Hmm. Did I get my numbers wrong? 0.385 divided by 0.5517. Everything looks to be off by a factor of 10, and I'm trying to figure out why. 1.53 kilograms, that's right. 1.53 times 0.33. Was that really 4.95? Yeah, that's 4.95. That works. I'm looking actually at the problem your book has. It's the same problem we worked, and evidently, I mean, I did this right yesterday, but for some reason I'm off by, it looks like a factor of 10. I'm trying to figure out why. Was it 3.85? Yeah, 4.95 minus 1.10 is definitely 3.85. And then I divided that by, I had to add the new uh, constant in front of alpha, which the 0.5049 was what I got for that kilograms times meters. That's 1.53. Let me see, 1.53 times 0.33. That's 0.5049, and then times 0.33 again. That gave me 0.1667. That looks fine. And then when I added the 0.1667 to the 0.385, that gave me 0.5517. That works fine. And then I'm taking the 3.8. That's why. I think divided by 0.5517. That was the problem. When I punched it in my calculator, this number looks right and everything. The number that I have here, that's all correct. But the problem is when I typed it into my calculator, I put it into 0.385 instead of the 3.85 because I remembered that the moment of inertia was 0.385 and I thought I was dividing that. So that's the problem. Let me correct that real quick. Everything, all the physics done was correct, so it's not a problem with that. The problem is a stupid arithmetic calculator error, and specifically the way I fix it is the following. And actually, I got to fix this one too. So now what's going to happen is I'm going to put in a decimal at the appropriate place, and then I'm putting it in black so y'all can see the difference there. But that's really what it is. So you can see the only difference was I actually typed it into the calculator as 0.385 divided by 0.5517 instead of 3.85 divided by 0.5517. Anybody have any questions on that? Or does Nathan have any questions on that? Sorry about that screw up here. Here's a much easier but interesting problem that has some pretty neat consequences. So this is example 1012, a rotating rod. It says a uniform rod of mass big M and length script L can pivot freely, i.e. we ignore friction, about a hinge or a pin attached to the case of a large machine, as in figure 1024. The rod is held horizontally and then released. At the moment of release, and they're just talking about just that moment, at the moment of release, because we can't analyze it any further without solving a differential equation. But at the moment of release, when you are no longer exerting a force holding it up, determine A, the angular acceleration of the rod, and B, the linear acceleration of the tip of the rod. Assume the force of gravity acts at the center of mass of the rod as shown. And that's reality. That's part of what we're trying to slowly work up to. Is I was telling you, where now that we have discussed torque, we can now start treating physical bodies as something other than point particles, as points in space instead of having them just infinitesimal points. They can actually have some structure because now we know how to deal with it. If we have a force on one end and a different force on the other end, before, if it's a point particle, if we have two forces acting on it, they just add. But we can't just add those two forces like that without understanding something about torque. So now that we have torque, we can figure bodies this way. In order to make sense of that, though, we have to treat the object, if we're wanting to figure out like its linear motion or something like that, we'll treat it as if it's subjected to forces at its center of mass, and then we'll have to treat its rotation as a separate physical problem using the equations of the summation of the torque equals I times alpha and stuff like that. But the F equals ma will still apply to the center of mass of the object. So for instance, when I throw a pin like this instead of a point particle, we know a point particle, if I throw it, it's going to have that nice parabolic trajectory. But if I throw a pin like this, then what we'll find, if we were able to video it and watch closely, and this had some, easy marks on it that could tell us what's going on, what we would see is there's one spot somewhere along this pin that as it flies, that one spot appears to do nothing but rotate instead of, it's translating as well, but it's just rotating such that the pin is rotating around that. That one spot that follows that parabolic trajectory is the center of mass of the object. And we have F equals ma and the projectile motion problem equations that we use to figure out how that center of mass behaves. But if we really wanted to know, hey, when it lands, what's the orientation of the pin, then we're going to have to use the summation of the torques equals I times alpha and have a reasonable explanation of exactly what the initial angle the pin made with, say, the vertical or the horizontal, and what was the initial angular speed that it had. And we'd have to take into account, is there air resistance? Is that slowing down that angular speed? Is that speeding up that angular speed? That sort of thing. And we'd have to follow all that. But the big picture is you've got to assume all the forces act on the body at its center of mass, and then you can deal with the rotation. So what we show here is the only force acting really is the force of gravity. There's a pin force that's holding that other end up, but that's just to hold the end up. And we're not trying to analyze this rod as if it's falling straight down. We're just saying it's sitting like this and it's going to fall like that. So what we need for this is solution. The summation, the torques is equal to I times alpha. This can be a inertial reference frame, because we're just basically taking a reference frame or a coordinate system that's tied to that pin, for instance. And with that, in this case, we're going to treat clockwise rotation as positive because it's the only rotation we have. It's the only torque we have. Why would I just have a random negative number everywhere or negative sign everywhere when I can have a positive sign everywhere? So that's what I'm going to do. With that in mind, we remember that torque can be given by R perpendicular times F. It can be given by F perpendicular times R. It can be given by R times F times the sine of the angle between them when they're tail to tail. And it can be given by torque is equal to R cross F. We don't really need the R cross F here. And not only that, if you notice, I've drawn the lever arm here, and you can see that the lever arm is horizontal and the weight is vertical, so those two are perpendicular to each other. So this times this and r this times this r this times this all give just F times R. Okay, so with that in mind, we can go ahead and say the only torque acting on this is going to be the force mg times the lever arm, which, notice the distance from the pin to the center of mass is L over 2. So we're going to say M times G is the force and L over 2 is the lever arm. And that's equal to the moment of inertia of the rod times alpha. And last time we actually derived for a uniform rod, we derived the moment of inertia for a uniform rod. Rotated about its center was 1/12 ml squared, but rotated about the end like we're doing here, that's supposed to be 1/3 ml squared. So I'm also going to use I rod end is equal to 1/3 ml squared in this case. Okay, so using the torque, the summation of the torques, which we have written down now, is equal to I times alpha. That means the I is going to be 1/3 ml squared, and the alpha, which is what we're looking for, is just alpha there. And as we said, we're looking for alpha and then we're looking for A for the tip. So at this point, we can see that the M cancels out with the M. We can also see that one of these L's cancels out with this L. And we can go ahead and solve for alpha. And what we'll see is alpha turns out to be 3/2, because there's a 1/2 all the way over there on the other side of the fraction, on the other side of the equation, and the 3 becomes goes on the top, and then it's going to be times a g. But then, in addition to times a g, it's going to be divided by an L, so it actually might be better to write it as 3/2 g over L is the angular acceleration of this. That's the answer. Now, we're also going to make use of the fact that A is equal to R times alpha. And because of that, we can say the acceleration of the tip is going to be L. That's the radius of the rotation that we're doing here, or the radius of the revolution that we're doing here, times alpha, which is 3/2 G over L, like that. And now you can see that the L cancels out with the L. And in this case, we end up getting that the linear acceleration of the tip is in fact 1.5 times g. So I mentioned that this had some interesting repercussions. Uh, you might be surprised to learn how many people actually get injured per year from, cutting down trees and then having the tree literally fall on them. This is part of the reason. When a tree falls, the tree itself behaves like an object, right? And what we've learned is that from physics, where we learned that when a force acts on an object, it behaves as if all of that force acts on the center of mass. So what's going on when you drop a tree is, normally a tree, one, for starters, it has a heavier base. The trunk is usually larger at the bottom, so that means it's heavier at the bottom than it is at the top. Not only that, as you go up, it does have limbs sticking out, but the limbs at the bottom are usually longer than the limbs at the top, and the limbs at the bottom are usually bigger around than the limbs at the top. So all of that points to the actual center of mass being a little bit less than halfway up the tree. So if you have a 200-foot tree, it's only going to be a little bit less than 100 feet up from the ground that the center of mass is. So when the gravity pulls on that, gravity is going to pull on that and try to make it accelerate at g. But because this is twice as far, and in fact for a tree it's more than twice as far out, that's going to accelerate at a greater rate than g, and it's very deceiving because you're used to seeing things fall at a certain rate, but the end of the tree comes down really fast. And yeah, that can be part of the explanation of why so many people do it. Then there's a whole idea of maybe people are not practicing the best practices when they're out cutting down trees. If you're doing it in your backyard with some friends and stuff like that, maybe there have been some intoxicating beverages drinking something like that. That would be really bad. All right. So that's example 1012. Any questions on that, Nathan? Exciting time to be alive, isn't it? All right. Now we're going to do another example of a moment of inertia calculation. So for a solution, we need the moment of inertia I is given by the integral of r squared dm. But what I have here is what I call Mr. Younger's example. It says, consider a thick washer-shaped hollow cylinder of mass big M, inner radius r1, outer radius r2, thickness h, that has a density rho of as a function of r is equal to some constant k times r. So what we're imagining here is like maybe the innermost level is made out of balsa wood, and then the next level is made out of a little thicker, a little more dense wood, maybe let's say cherry or something like that. And then out further is spruce pine fir, and then out further is southern yellow pine, and then out further maybe it goes to aluminum, and then out further maybe it goes to copper, and then out further maybe it goes to steel. By doing that in that way, it might not be a smooth, continuous function, but it could be if you played with the numbers right, or if you played with the mixtures and you found some way to bond wood to metal and stuff like that and different woods together, you could ultimately get a profile that would make the weight per unit volume of this washer get heavier and heavier as the farther you go out. That's what that's supposed to be representing, rho equals k times r. It could also be something as simple as maybe the washer, instead of it being a washer, maybe it's not a perfect cylinder of fixed thickness. Maybe at the inner radius it has one thickness, but then it gets bigger as you go out. That's another way that you could compensate for it, because if it gets thicker this way, that's not changing the moment of inertia except through its mass. So you can sort of estimate that changing of the shape as a change in the density. So that's another way you could do it. Now, given that argument, I'm asking you to compute K in terms of M, R1, R2, and H, and specify the units of K. So we are going to do that. But now let me go ahead and write down the solution. We needed I equals integral of r squared dm. Of course, we told you that whenever you use I equals integral of r squared dm, or the center of mass is equal to the integral of x dm over the integral of dm, or the center of mass in the y direction equals the integral of y dm over the integral of dm. Whenever you use that dm, it's either going to be a lambda times a dl, or it's going to be a sigma times the differential area element, or it's going to be a rho times the differential volume element. One of those three. That's what it is. And when they say it's a uniform object, then that means the lambda, if you're using that, or the sigma, if you're using that, or the rho, if you're using that, is supposed to be a constant. This is not that scenario. This is a scenario where it's clearly not uniform. So I'm upping the ante and having you solve a little bit more complex problem than typically done. So there's what our DMs are. But I also want to point out that we have to know, for instance, what the units of K are. And we can do that from the formula that we get when we solve part A. But we can also do it just by looking at rho of R is equal to K times R, because rho is a density. It's a mass per unit volume. So it literally should have units of kilograms per cubic meter. And what we're saying here is when I multiply K times R, I'm supposed to have kilograms per cubic meter. And R has units of meters. So in order for that to happen, the K must have units of kilograms per meter to the fourth. So that's what we suspect the units of K should be. They should be kilograms per meter to the fourth. So it's always good to try to predict an answer beforehand, and then you can pat yourself on the back when you do the calculation and get the right answer. Now, uh, when we go to tackle an integral like I equals integral of r squared dm, the main thing is the integrand, in this case, the r squared and the dm to some extent, but the r squared dm, that can't vary very much. That value r can't vary but by infinitesimal amount from one edge of the dm to the other edge of the dm, because if you did, you would have to figure out some way of computing like the average dm or something like that, or the average r for that dm or something. So it's best to try to make the r vary very little over the whole structure of the dm. So what I'm choosing for my dm is going to be rho dv, and then what I'm choosing for my db is basically a little narrow slice on top that's basically like a circle inside of a circle, right? And then it's going to have a thickness h. So normally in your Calc 2 class, or maybe you did it in Calc 1, you would normally say that's 2 pi rdr would be the area of that little green racetrack on top of it. That would normally be what we call it, 2 pi rdr, because it looks like the inner radius would give us the r, and therefore the distance around would be 2 pi r. And if we just multiplied that distance around by dr, then we get basically the area of a rectangle whose length is 2 pi r and whose width is dr. But that's not really what we have, even when we're looking at that dA, because if we actually cut that, we would actually have the inner part only being a length 2 pi r, but the outer part would have a length of 2 pi parentheses r plus dr. So it's not technically a rectangle. It's more like a rectangle with little triangular ends on it. Uh, but we always use the 2 pi rdr, and the reason is because you're taking infinite sum, a Riemann sum, as the dr gets infinitesimally small. And the difference between 2 pi rdr and what the real formula is, the real formula, of course, would be pi pi times parentheses r plus dr close parentheses squared minus pi r squared. That's the real formula. But if you calculate that, you're going to see that that only differs from 2 pi r dr by an amount on the order of dr squared. So it doesn't matter. The same thing happens with this when we're doing the volume. It would normally be pi r squared h would be the volume of the cylinder. But in this case, it's a cylinder minus a cylinder. So it'd be pi parentheses r plus dr close parentheses squared times h minus pi r squared h. When you do that, you're going to see that they're only going to differ from the 2 pi r h dr by an amount that's proportional to the square of the dr, and therefore we can toss it out. In the video from last night, if you want to look at that, I actually proved that the two are equivalent up to order of dr squared. So you can look at that if you want, but you don't have to. I'm just going to go with it. So what I'm going to say right here is our differential mass element is that green shape that we see in here. So this dm is equal to rho dv, like I already had written up there, but the dv is going to be 2 pi h times r times dr. So that's what we're really using. Now I'm going to go ahead and start part A, and part A is where we're trying to determine what K is. What we know is the integral of dm has to equal m. That's what we're going to use. Therefore, we can say m is equal to the integral of dm, which equals the integral of rho of r dv, which equals the integral of k times r, that's my rho of r, and then my dv is 2 pi r h dr, like that. And I'm going to integrate from r1 to r2. Okay. So with that in mind, I can go ahead and pull all the constants out in front, and those constants are 2 pi hk, and then we have times the integral. I now have two r's in there. That's going to be r squared dr, and I'm integrating that from r1 to r2, making sure I got everything. I see there's a 2, there's a pi, there's a h, there's a k. I got all those, and I got r times r, that's r squared. So that's all good. So all this looks right to me. Now I can go ahead and integrate that. The integral of r squared is 1/3 r cubed. So this is now going to become 2 pi h k over 3, and then it's r cubed, so that's going to be r2 cubed minus r1 cubed. Oops. R1 cubed, like that. And that is all equal to m. Because that's equal to m, we can now solve for k, and we'll see that k is equal to 3m over 2 pi h times r2 cubed minus r1 cubed, like that. And that's what our actual k value is. Not only that, we can see from that that the dimensions of k, or the units of k, is clearly going to be, notice I have meter, or I have an m in the top, so that's the kilograms, and then I have a h times a r cubed minus an r cubed, so that's r to the fourth, basically, or meters to the fourth. So this is kilograms over meters to the fourth, and that's exactly what we predicted, so we feel pretty good about that. Anybody have any questions on that part? Okay, so that's a little bit more advanced than normally we give as a example, but I wanted you to really see, taking all the parts out and showing how you could do it and how you can make it more complicated and stuff like that. I could now go and say, what about if rho of r was k times r squared, or what if rho of r was k times r cubed, or something like that? You could make it even more complicated that way, but it's not really that much more complicated. The integrals are straightforward. It's r to the power, and whatever the power is, you add 1 to it and divide by that number. So that's pretty straightforward. Now that we have k, we can use that k a little later, when we go to calculate the moment of inertia, because the moment of inertia is going to come out in terms of k, but we weren't given k. We were given capital M, R1, R2, and H. So any answers we have should come out in terms of M, R1, R2, and H, not k. So now I'm going to go ahead and calculate the moment of inertia, and that's part B. So the moment of inertia is equal to the integral of r squared dm. And of course, that's the integral of r squared. And then dm is rho dv. And then that equals the integral of r squared kr times 2 pi r h dr, like that, because that's our differential volume element. It's 2 pi h r dr. So now we see we have a r squared, r times the k, and then we have another r in the formula. So in fact, we have r to the fourth power here. So with that in mind, we can pull out all the constants. That's going to be 2 pi hk. All of that's out in front, and now we're going to get the integral of r to the 1, 2, 3, 4, r to the fourth dr, from r equals r1 to r equals r2. And of course, the integral of r to the fourth is 1/5 r to the fifth. So this is going to give us a formula of 2 pi hk over 5 times r to the 2, or r2 to the fifth power, minus r1 to the fifth power, like that. Now that is in terms of k, so that's not very helpful to us, but we can go ahead and put in the k. I'm going to say this is 2 pi h r2 to the fifth minus r1 to the fifth, all of that divided by 5. And now I'm going to plug in my k, and my k was 3m over 2 pi h r2 cubed minus r1 cubed, like that. Now you can see the 2 pi h cancels out with the 2 pi h, which is really wonderful. And ultimately, we end up getting, very simply, 3 fifths m times r2 minus r1 to the fifth power over r2, oops, over r2 to the third power minus r1 to the third power. So our moment of inertia is in fact 3 fifths m r2 to the fifth minus r1 to the fifth over r2 to the third minus r1 to the third. And you can see that sort of looks like the normal formula. The normal formula is some number times m times some dimension like L or radius squared. And you can see that this fits that bill because it's r to the fifth over r to the third, and r to the fifth divided by r to the third gives you r to the two. So it's just like ml squared. But that is the moment of inertia for this complex washer that has a intensely increasing density uh, that increases with the value of R. Any questions on that, Nathan? All right, so that's the kind of question that is a really great homework question, and in principle, it could be something that would pop up on a test or a final exam. I don't consider that too hard to do. However, that would be sort of a more advanced question that I would ask on a test. It's not one of the easy ones. That would be one that would be worth like 25 points as opposed to the normal 10, 15 points or something like that. All right. Now, what we can do is we're going to work on another problem. This is example 1015. By the way, your book does example 1013, and that's very much like this example, except it doesn't have, example 1013 doesn't have this variable density. So this is like, oops, I should put an E on that. This is like example 1013, except rho equals a constant in that example. Okay. It then does example 1014, which is a parallel axis theorem application. I've already given you a parallel axis theorem application, but this one's actually a more neat one, and it's so abstract that you might not realize that this can be done. So it's definitely something you want to look at and learn how to do. I'm just choosing not to cover it because I covered the parallel axis theorem before. The perpendicular axis theorem, well, for starters, it does give you a proof of the parallel axis theorem, which is kind of helpful. And you are responsible for knowing the parallel axis theorem, like I used in last class. But it also gives you the perpendicular axis theorem, even though it doesn't derive that for you. I am not going to test you on the perpendicular axis theorem. It's a little more complicated to apply. It's got very specific conditions that have to be met and stuff like that. That being said, I think I removed all the perpendicular axis theorem questions from the test banks as well as from the practice banks and the homeworks. So you shouldn't run into those, but if you do, I don't have a problem with you trying to learn how to use them. I'm just not going to test you on it. So it'll never appear, a perpendicular axis theorem problem will never appear on a face-to-face test, an online test, or any other kind of test for that matter, final exam. Okay. All right, now we're going to example 1015, which is in the next subsection, and we're talking specifically about rotational kinetic energy. So I showed you before that kinetic energy is 1/2 mv squared. That's what we learned in chapter, I think it was 8. Yeah, chapter 8. And the rotational analog to mass, of course, is moment of inertia, and the rotational analog to velocity is omega. So it would seem reasonable that if k is equal to 1/2 mv squared, then k rotational would be 1/2 I omega squared. And that's true. That is the rotational analog. But if you have, for instance, this pin going straight like this, then the kinetic energy is just 1/2 mv squared. But if you have this pin doing like this, rotating at some fixed omega or whatever as it's moving this way, then you have a 1/2 mv squared for the velocity of the center of mass of the pin. So remember, it's spinning like this, but the center of mass is moving at some velocity vcm. That's the kinetic energy of the object moving linearly is 1/2 mv squared, but it's also rotating about its axis, so it has a 1/2 I omega squared as well. And if you're fortunate enough to know that the rotation rate is such that, like if you're rolling without slipping, then if you're talking about a ball instead of a pin, you're talking about a ball rolling along an incline. The center of mass is moving, and that has, as the whole body moves linearly, has a kinetic energy 1/2 mv squared. But it, as it's rotating, it also has a 1/2 I omega squared. But if it's rolling without slipping, then there's a linkage between the v center of mass and the omega. Specifically, rolling without slipping means the v center of mass is equal to the radius of the object times the omega that it has. So that's something to keep in mind. Now we're going to start with a very simple one or actually very simple two, where we're just going to have objects rotating about some point as opposed to translating and rotating. So these first two examples are about that. Example 1015, for instance, says flywheel. Flywheels, which are simply large rotating disks, have been suggested as a means of storing energy for solar powered generating systems. Estimate the kinetic energy that can be stored in a 80,000 kilogram flywheel with a diameter of 10 meters, i.e., the size of a 3-story building. Assume it could hold together without flying apart due to internal stresses at 100 RPMs. Okay, so solution, it is a large rotating disk. So the moment of inertia for a disk we know is 1/2 mr squared. We also know that the kinetic energy of rotation, this is just the rotation part, and that's all that's happening with this one. This one's not translating, it's just rotating. So that's 1/2 I omega squared, like that. We have the fact that it's 80,000 kilograms. Remember, 1,000 kilograms is what we call a ton. It's actually called a metric ton, and it's about 2,200 pounds, whereas a short ton or a US ton is 2,000 pounds flat. Okay, so this is a really, really heavy thing. Now, let's calculate that energy. The kinetic energy is equal to 1/2 I omega squared, but I is equal to 1/2 mr squared. So I'm going to put in 1/2 m times r squared. And then all of that is going to be multiplied by omega squared, which is 100 revolutions per minute. But we've got to convert that because revolutions is not a unit that works out to give us joules. We're going to have to compute that as radians. And not only that, minutes is not a unit of time that works out to be joules. So we're going to have to convert that to seconds. But what we have is 1/2 times 1/2, which is 1/4. We also have the mass, which is 80,000 kilograms. And then we have the radius, which is 5.00 meters, and that's got to be squared. And then we have the uh, omega squared, but I needed more space to convert that, so I didn't put in the number right now. So now I've got 1/4 times 80,000 kilograms times 5.00 meters squared times, now we're going to put the 100 revolutions per minute here. I'm going to first get rid of the revolution because we know one revolution is equal to 2 pi radians. And now I'm going to get rid of the minute because we know 1 minute is equal to 60 seconds. And now all that quantity has to be squared. So we're going to go ahead and say 0.25, that's the 1/4, times 80,000 times 5 squared times, now I'm going to put this in parentheses, 100 times 2 times 3.14159 times, or actually I should say divided by 60, close parentheses, and now I'm squaring that, and that should give me 5.48 times 10 to the 1, 2, 3, 4, 5, 6, 7. And at best, we had two sig figs here, maybe. So I should probably underline that. But we now have the units are in joules. And of course, we could convert this to kilowatt hours to see whether that's a significant amount of energy. And what we'd find out is it's not very impressive. A typical power plant, for instance, is on the order of a gigawatt. Is a typical one. That's 10 to the ninth joules every second. So in this case, we're talking 10 to the seventh. That's not a very huge amount of energy. But that being said, it is a viable option for storing energy. It just maybe is not easy to get one as big as we'd like. Uh, any questions on that? All right, now we're going to look at example 1016, and this is a rotating rod. A rod of mass M is pivoted on a frictionless hinge at one end as shown in figure 1030. The rod is held at rest horizontally and then released. Determine the angular velocity of the rod when it reaches the vertical position and the speed of the rod's tip at this moment. So this is sort of like that problem we did right here. And remember, I said I couldn't solve that because that would actually entail us solving a differential equation that's not that easy to deal with. Uh, but guess what? Using conservation of energy methods, we can at least figure out how fast it'll be going when it reaches the vertical position because this thing's actually falling like this and it's going to fall into a vertical configuration. So that's what we're doing with this problem 1016. So let's write down solution. What we're going to use is conservation of energy, and my version of conservation of energy is U initial plus K initial plus work in is equal to U final plus K final plus work out plus E loss. But we're assuming there's no friction to deal with here, so we're going to ignore friction. So that would normally entail us in calculating E loss. We're not going to be compressing any springs. Nobody's going to be putting any work into it, like a father pushing a daughter on a mountain or anything like that. So these terms are all going to be zero. And not only that, if we choose to call the height basically L over 2 below the center line of the beam, if we call that height U equals 0, then the potential energy at the end would be 0. So I can go ahead and say U final is equal to 0. And we are dropping this from rest, so K initial is also 0. So as often happens with conservation of energy, you're just applying a very simple part of it, only in this case, two terms. So you don't normally have, three terms on one side and four terms on the other, though you could have. Most of the time, it's usually just one term and one term, or two terms and one term, or something like that. So now let's go ahead and put what those terms are. Well, we know we're close to the surface of the Earth and we're not changing significantly from one part to the other on the order of the fraction of the radius of the Earth. So mgh is our potential energy. So I'm going to start off by saying the initial potential energy is the mass of the rod times g times specifically a height of L over 2 because we're saying L over 2 down from that is U equals 0. So the height up is L over 2. So that's our kinetic, or excuse me, that's our potential energy initially. Now our kinetic energy finally, in this case, the object's not actually moving translationally. It's just rotating this way. So it only has 1 half I omega squared energy. So in this case, it's going to be 1 half I omega squared like that, but it's a rod rotating about its end, so rod end is equal to 1/3 ml squared like that. So now I can plug that in. I'm going to get mgl over 2 is equal to over 2 1/3. Oops, that's supposed to be a 1/3. 1/3 ml squared times omega squared like that. Now you can see that the m's drop out and the 2's drop out, and one of these exponents on the L is going to cancel out the L on this side. So from this, I get only G on the left, but on the right, I get 1/3 G times L, or excuse me, 1/3. I don't know where that G came from there. 1/3 L times omega squared there. So solving for omega, I find that omega is equal to the square root of 3GL, like that. So that's what the omega would actually be. And if you wanted to calculate the velocity of the tip, V tip is equal to the whole length, which would be L, because we're using V equals R times omega, but the R in this case is L. So V tip would be L times omega like that. We have the omega is the square root of 3GL. Now we can say that V tip is equal to L times the square root of 3GL. Of course, when you multiply L by a square root, you can pull it inside by squaring it if you wanted to. Actually, let me see. V equals R omega. That works okay. That's just 3GL. And wait a second. That 3GL is wrong. Oh, it's 3G over L. That's what it was. Catch my algebra there. Did you notice that algebra mistake, Nathan? I completely made a boo-boo. The L comes to the bottom. And if I would have looked at the units for a split second, I would have known that it came out that way. But omega is going to be the square root of 3G over L, not 3GL. Notice the L is canceling out the meters in the G, and we'd have the square root of 3G over L is the 3 square root of 3 radians per second squared, and you could call that radians squared per second squared if you want, so that you, when you take the square root, you get it radians per second, or in this case, just radians per second. But that's really what the angular velocity is. Now I'm going to use, as I said, V equals R omega tells me that V tip is equal to L times omega, which equals the square, excuse me, which equals L times the square root of 3G over L. If you wish to pull the L inside the square root, all you have to do is square it. So this is going to become square root of 3G L squared over L, like that. That's an L down the bottom. So finally, I get the velocity of the tip is equal to the square root of 3GL, like that. And you might notice that when an object falls, like just straight down, what would its velocity be? Well, using conservation of energy, UI plus KI plus work in is equal to U final plus K final plus work out plus E loss. If I was just to imagining an object of mass m falling a distance L over 2, then what I would have is m G L over 2 is equal to 1 half M V squared. You can see that the M's cancel out, the 2's cancel out, and in fact, you end up getting specifically V is equal to the square root of G times L, which notice in this case it's markedly faster. It's a square root of 3 times faster. So it's about 1.73 times as fast as if you just dropped an object a distance L over 2. That's all because the tip, again, is being accelerated greater than the acceleration of gravity, just like the top of the tree would be, or just like that previous rod would be. Any questions on that? All right. So now we've done some fairly straightforward kinematic slash dynamic problems. We want to get a little bit bigger ones, ones that involve not only rotation but translation. So motion left, right, in, out, or up, down, in addition to rotation motion. That's translational, is that left, right, up, down, in, out stuff. So we're going to go to our next example, which is example 1017. So example 1017, I will pull it up here and read it for you. It says sphere rolling down an incline. What will be the speed of the center of mass of a uniform solid sphere of mass m and radius r0 when it reaches the bottom of an incline if it starts from rest at a vertical height h and rolls without slipping? Excuse me, and rolls without slipping. See figure 1034. Assume no slipping occurs because there's plenty of static friction. Compare your results to that for an object sliding down a frictionless inclined plane. So that's what we're trying to do here. I've drawn the diagram. I've went ahead and written down the variables we know. We assume the mass, capital M, we know. We assume the radius, R0, we know. We assume the height of the incline, H, we know. We probably won't need it right now, but we also assume we know the angle of the incline is theta, and we're asked to find the velocity of the center of mass when it reaches the bottom. We are, of course, told that omega 0 is equal to 0 and v0 is equal to 0. I didn't really include that. We're also told that it's a uniform solid sphere, and the moment of inertia for a uniform solid sphere is 2/5 mr0 squared. I just happen to know that from deriving it a billion times. So, solution, we're going to use conservation of energy again here. So, solution, we're going to start with U initial plus K initial plus work in is equal to U final plus K final. That's a really weak looking K plus work out plus E loss. Now, in this case, it's kind of odd, but we have to have significant friction for it to roll without slipping, but at the same time, we're ignoring friction. So in reality, we're actually going to have it friction affect it, but we're going to assume the energy loss is zero. So I'm going to say E loss is zero. I'm going to say the work out is zero. I'm going to say the work in is zero for the same obvious reasons that we normally argue it. We also know that it's starting from rest, so K initial is zero. Now, here's the big thing. Technically, the center of mass of that ball is up a height h plus r0, right? But if I chose to say the zero of height, if I chose to ignore that part and say we're just trying to measure it to the bottom of the ball, long as we consistently measure it to the bottom of the ball, that's fine too, right? Because the center of mass is always going to be an amount r0 above it. So it's basically like moving my coordinate system from u equals 0 here to u equals 0 here, which is 0 plus r0, right? So I'm going to treat it as if the zero of potential is when the bottom of the ball reaches the bottom of the incline. So with that in mind, I can go ahead and plug my values in. I'm going to have the mass of the ball times g times the height, which is h, and of course that's the height to the bottom of the ball. And then the right hand side is going to be the potential energy. And since I chose to make this particular line
U equals zero, then the potential energy at the end is zero. Now, here's the kicker. The kinetic energy is the kinetic energy of the ball's center of mass moving like that, as well as the kinetic energy of the ball rotating about its center. So I don't have a single term for kinetic energy. I have two terms. I have 1/2 mv squared. So 1/2 mv, and that's technically v center of mass squared, plus I have 1/2 I omega squared. Now, since it's rolling without slipping, rolling without slipping implies that v center of mass is equal to r0 times omega. So that makes it a little easier for us. Now I can go ahead and plug in mgh is equal to 1/2 m v center of mass squared plus 1/2. Now I'm going to put in 2/5 mr0 squared for the moment of inertia. And then in place of omega, I'm going to put in v center of mass over r0. So that's v center of mass over r0, but it's got to be squared still. So now what you see is when I square that r0 in the bottom, that's going to cancel out the r0 up here. And that's going to give me, in fact, well, let's go ahead and write it again. I'm going to say now I have mgh is equal to 1/2 mv center of mass squared plus 1/2 times 2/5 is going to give me 1/5, and then mv center of mass squared. This is 1/5 plus 1/2. So 1/2 is, of course, 5/10, and 1/5, of course, is 2/10. So 5/10 plus 2/10 is 7/10. So I get 7/10 mv center of mass squared. And now we can see that the mass cancels out with the mass over here, and we can solve for the v center of mass, and we get specifically the velocity of the center of mass is equal to 10 over 7 times g times h square root. So that's the velocity that it'll have at the bottom. It's roughly 10/7 times g times h. Now, if we were to consider an object sliding without friction down the same incline, an object slides down from rest without friction, then conservation of energy would give us mgh is equal to 1/2 mv squared. You can see again the m's are canceling out, but this time the v is equal to the square root of 2gh. That's capital H. Sorry about that. Might as well just rewrite it. Square root of 2gh, like that. So you see that when the object slid down, it was going the square root of 2gh, but when the object rolled down, it went down the square root of 10/7 gh. Now, if it was 14/7, then it would be exactly the same. So we're actually 3/7, square root of 3/7 smaller than that. And that's basically the price we paid for some of the energy going into rotating the sphere instead of just letting it slide down without friction. So, any questions on that one, Nathan? All right. Now, your book does a really nice example, conceptual example 1018, and then it does another example Actually, no, the 1019 is the one I want to do. We're going to skip the example 1017, or excuse me, 1018. It just says which is fastest. Several objects roll without slipping down an incline of vertical height h, all starting from rest at the same moment. At the same moment, the objects are a thin hoop or a plain wedding band, a spherical marble, a solid cylinder like a D-cell battery, and an empty soup can. In addition, a greased box slides down without friction. In what order do they reach the bottom of the incline? All the objects, excuse me, have the same mass m and radius r if they're rolling. Okay, so it's a really nice problem, but what you see is basically the object with the largest moment of inertia is going to go slowest because it's stealing some of that energy. We had 1/2 plus 2/5 times 1/2 as a result of it being a sphere. But if you had, for instance, a D cell battery, then it's 1/2 mr squared. So that's 1/2 times 1/2 would be 1/4, and then 1/4 plus 2/4, which is what 1/2 is 3/4. So you're going to get in that case a 3/4 in front of the g times h. So you see that in fact the objects with the larger moments of inertia are going to go down slower. So the fastest thing, of course, would be the box without friction. The next fastest thing would be the sphere because that's 2/5 mr squared. 2/5 is zero point 0.4. Then the solid cylinder, which is 1/2 mr squared. The empty can, which is pretty much mr squared, and our yeah, the empty can would be essentially somewhere between mr squared and 1/2 mr squared. And then the hoop or wedding band would just be mr squared. So you'd expect them to go down in that order. The box sliding first, then the sphere, then the solid cylinder or the D-cell battery, then the empty soup can, and then the wedding ring. So again, I'm not going to discuss that more than what I just did, but we're going to go on to now example 1019. So 1019 is the exact same problem we did last time, except now we're going to see if we can calculate the acceleration this thing's going to get by using our dynamical equations. We're going to use Newton's second law of motion. We're going to use Newton's second law of motion for rotation. And in fact, because we're going to tie a coordinate system to the ball as it goes down the incline, that's an accelerating reference frame. And an accelerating reference frame means that we only have one version of Newton's second law for rotation to use, and that is the summation of the torques about the center of mass is equal to I about the center of mass times alpha about the center of mass. That's the only version we can use. And the reason why we can use it is because the axis stays in a fixed direction. It's always out of the plane of the page, perpendicular to it, and it stays in that direction. Now, if the ball was actually rolling down like that, then that equation wouldn't actually apply. But we're assuming that that's going to happen and it's going to smoothly roll down it so that the axis stays the same, and we can use that. So here's the problem. Analyze the rolling sphere of example 1017, see figure below, in terms of forces and torques. Determine the velocity VCM of the sphere's center of mass at the base of the incline and the magnitude of the friction force, F friction. So that's what we want is the friction force, and we want the VCM. So what we know is omega zero, the initial angular velocity is zero. We know V zero is also zero. We also know specifically that we're asked to find VCM at the bottom, and we're asked to find the friction force required to allow it to roll without slipping. And all of this is rolling without slipping. And of course, rolling without slipping implies that V center of mass is equal to the radius, which we called the radius before R0. So that's going to be R0 times omega. So that's something we can use as well. Solution. We're going to need some stuff. We're going to use Newton's second law of motion. The summation of forces is equal to mass times acceleration. We're going to use Newton's second law for rotation, and that's the summation of the torques about the center of mass is equal to the moment of inertia about the center of mass times the angular rotation about the center of mass, because that's the only version we can use because we're having a coordinate system that's accelerating down the incline. And now, in addition to that, we know that it's a sphere, it's a uniform sphere. So I for the sphere is equal to 2/5 m r0 squared. And of course, we assume we know m as well. So that's covered too. So we know m, we know h, we know theta, and that's pretty much it. Yeah, that's it. So I've drawn the forces acting on the ball as you see them here, and you can see I've tilted my coordinate system. That x-axis is supposed to be parallel to the hypotenuse. It's a little bit off of parallel, but that's just my drawing. It didn't come out as well as it's supposed to be, but we're assuming that it's going to do that. Now I'm going to take the summation of the forces in the y direction equals mass times acceleration in the y direction. I know that's supposed to be a y, and it turned out to look like an x. Actually, let me get that back here. So the summation of forces in the y direction equals mass times acceleration in the y direction. Now, this object's going to be rolling down this incline, and the y is perpendicular to the plane. So the actual position of the center of mass of the ball is not going to have a changing y at all. Since the y is not changing, the velocity in the y direction is zero. And since the velocity in the y direction is zero, and then it's still zero, and then it's still zero, that means the acceleration in the y direction is going to be zero as well. So we don't need the right hand side. It's just going to be equal to zero. I shouldn't say I don't need it. It's just the right hand side is zero. Now, in addition to that, we've got to break down this force, which is the weight. We've got to break that down into components parallel to the y-axis and parallel to the z-axis. So if I allowed my x-axis or my y-axis to continue down this way, and then I allowed my x-axis to be shown this way, then I can see that the mg would be broken down into two components, a negative y component, which is right here, and a positive x component, which is right here. This is just something we've done repeatedly now since we got to chapter 3, or actually chapter 4. And we know that specifically this forms a right triangle and this angle's theta. So this angle must be 90 minus theta. Well, this angle from here to here is 90, so this angle must be 90 minus parentheses 90 minus theta, and 90 minus parentheses 90 minus theta in parentheses is just theta. So that's why I have that theta right there. That is the angle up there, and that tells us specifically that this component is mg cosine theta, and this component down here is mg sine theta. And we don't necessarily need it. Like if we wanted to compute what the center of, or excuse me, what the moment of, or wrong, wrong variable again. If we wanted to know what the coefficient of friction was, specifically the coefficient of static friction was on this, then we could solve for the normal force. And that's all this equation in the y direction is going to give us. But I'm going to use it anyways just to show you. So with this one in mind, I'm going to get Fn, which is pointing up, minus mg cosine theta, which is pointing down, is equal to it's equal to zero, as I explained earlier. So that just tells us that the normal force is just equal to mg cosine theta. We don't really need that. I didn't need that. That was more in case we want to figure out what the mu is. But we do need the summation of the forces in the x direction equals mass times acceleration in the x direction. Now, this acceleration is going to be real, and it's going to be the acceleration down the incline. If we happen to get that's a constant, then we can use kinematic equations to figure out, once we have that acceleration, exactly what the velocity will be. If it's not a constant acceleration, in principle, we can figure that out too by the integration process that we used in chapter two to derive the kinematic equations, but it's not going to be necessary. So what we see here is the summation of forces in the x direction. I really only have one force acting in the positive x direction, and that's the mg sine theta. That's the component of the weight that pulls it down the incline. So that's going to be mg sine theta. And now I have minus the friction force, which is acting up the incline because its intent is to stop the relative motion. That's the way friction works, is it tries to impede relative motion. And in this case, the ball is trying to slide down the incline. It's instead trying to pull it back this way, which forces the ball to rotate. So all of that is equal to m times a, and that's going to be equation one. Now I'm going to take the summation of the torques about the center of mass is equal to I about the center of mass times alpha about the center of mass. And with this equation, we have to actually treat it as the center of mass is the axis going dead through center through the sphere. And with that in mind, I've drawn the mg attached to the center of mass of the ball because, as I told you, physical objects behave as if the weight or all the forces acting on it are acting at their center of mass if you're trying to figure out what their motion is, left, right, in, out, up, and down, right? The same thing with the normal force. The normal force actually goes right through the center of mass. In both cases, the lever arm is zero. So I've got a zero lever arm for the mg. I've got a zero lever arm for the normal force, but I have a lever arm for the friction force, and that lever arm is the radius of the sphere. And since the friction force is tangential to the sphere, that means the torque due to that friction force is actually a multiplication of the friction force times the radius, and that's it because they're perpendicular. So I'm going to treat that direction of rotation as a positive direction. And what we're going to say is the friction force times the radius, and we called the radius R0 if I remember correctly. The friction force times the radius R0 is equal to the moment of inertia for the sphere is 2/5 m R0 squared. And then the alpha is what goes on the end there. And this is, in fact, equation two. Now, I also have the equation A is equal to R0 times omega because it's rolling without slipping. I'm going to call that equation three. Oops, excuse me. I don't know why I wrote omega there. It's A equals R0 times alpha. So what I'm going to do at this point is I'm going to go ahead and substitute equation 3 into equation 2 to get rid of alpha. So plug 3 into 2 to eliminate alpha, introducing A. So that's what I'm going to do. That gives me F times R0 is equal to 2/5 m R0 squared times alpha, which becomes A over R0. So I get A over R0 like that. Now you can see that the R0 in the bottom is going to cancel out with the exponent of 2, leaving an exponent of 1. But then the R0 over here is going to cancel out the other R0. And this, in fact, gives us that F is equal to 2/5 m times A. I'm going to call this equation 4. Now I'm going to plug 4 into equation 1. If I plug 4 into equation 1, then I'm going to get mg sine theta minus 2/5 ma is equal to ma. Now, I'm ultimately going to try to solve for A, but right now I can see that the M's at least cancel out. So I can go ahead and get rid of those. But now I'm going to pull the 2/5 A to the right and it'll become positive, and I'm adding 2/5 to 5/5, which gives me 7/5. So this is going to give me G sine theta is equal to 2/5 plus 5/5 is 7/5. A like that, and therefore we find that A is actually equal to 5/7 G sine theta. What we learned previously was when an object slides down an incline with no friction, the acceleration is G sine theta. In this case, the acceleration is not G sine theta, it's 5/7 G sine theta, and that's why we get a velocity that's smaller than the square root of 2gh at the bottom. But that's it. We now have the acceleration, which wasn't what we were asked for, but the fact that it's a constant, it's 5/7 times g times the sine of the angle, none of that's changing. So that is a constant acceleration. Now we can use the velocity or one of the kinematic equations, since the acceleration is a constant, we can use one of the kinematic equations to figure out the velocity that it has at the end. Now, velocity equals initial velocity plus AT is not going to do us very good because the T we don't know. We'd have to compute the T first. But if we use the equation that some instructors don't allow their students to use, specifically V squared is equal to V0 squared plus 2A x minus x0. If we use that equation, then we can get what the final velocity would be at the bottom. Now, the distance traveled in this case is actually the hypotenuse. The hypotenuse of that triangle. Well, remember that triangle is h theta and I like that. So the hypotenuse, this distance right here, if we write sine theta, we get sine theta equals opposite, which is h, over hypotenuse, which is p. So this thing tells us that the hypotenuse is in fact h over sine theta. So that's the actual distance traveling down the incline. Specifically, the length of the hypotenuse is h over sine theta. So I can now use all that, and I'm going to do it as follows. V squared is equal to 0 squared plus 2 times A. A is 5/7 G sine theta. And then the hypotenuse is, of course, h over sine theta. And you see now that the sine theta in the denominator cancels out with the sine theta in the numerator. And you end up getting, in fact, the right-hand side is just equal to 2 times 5 is 10/7 times g times h. And therefore, V, the V of the center of mass, is equal to the square root of 10/7 G times H. And that was the result we were trying to get. Notice that's exactly the same velocity we got earlier when we did it by conservation of energy methods, specifically the square root of 10/7 times G times H. Now, the friction force, we learned that the friction force was 2/5 ma, so we can go ahead and say, in this case, the friction force is 2/5 m times a, and a was 5/7, so friction force is 2/5 m times a, and a was 5/7 G sine theta. So this all gives us that the friction force is in fact the 2/5 times the 5/7 gives us 2/7. So it's 2/7 mg sine theta is the friction force. Okay. Now, you could go about finding out the moment, or excuse me, the coefficient of friction. But remember, the way static friction is, it only supplies enough mu to get the thing to not move up to some maximum value. We have no idea whether this is at the borderline of breaking static friction loose or not. So we can't really say whether if I just set that equal to mu times mg cosine theta, we can't really say that that would necessarily give us the mu. That would give us a possible mu, but the mu could actually be a little bit larger. So that's why I'm not using that. But that's also the reason why I started with the summation of forces in the y direction equals mass times acceleration in the y direction in case we wanted the mu, but we didn't need that. So, any questions on that one, Nathan? This is one of my favorite problems. Just being able to see that these two entirely different ways of working the problem give you the exact same answer. We worked it with conservation of energy. We got the velocity at the bottom was the square root of 10 sevenths gh. Then we worked it with Newton's laws of motion, taking into account friction, and found out that the velocity is in fact the square root of 10 sevenths gh. So that's kind of cool, and it gave us a idea what the friction force is. So we know if the friction force is at least that large, then that's sufficient enough to keep it rotating. But it had to be 2/7 times mg times the sine of theta, where theta is the angle of the incline. So obviously, a larger incline angle. Up to 90 degrees, the sine keeps increasing, increasing, increasing up till it gets 90 degrees. And it doesn't make any sense to have a triangle or a wedge triangle shaped like that to have an angle bigger than 90 degrees. So we're just talking about up to 90. That means as you get closer and closer to 90, the friction force is going to have to be quite a bit larger. So it could get as high as 2/7 m times g. All right. I think that's the last of it. Let's see what else is going on. Yeah, oh no, that's right. I got one more problem I wanted to solve. This is example 1020. And yeah, we got 25 more minutes, so that's plenty of time. So example 1020, this is more advanced examples. And it says specifically, example 1020, a falling yo-yo. A string is wrapped around a uniform solid cylinder, something like a yo-yo, of mass big M and radius big R. And the cylinder starts falling from rest. As the cylinder falls, find A, the acceleration of its center of mass, and B, the tension in the string. So what I've done is draw the picture. That's what you see on the left here. And then I drew the free body diagram. That's what you see on the right. The variables that we assume we know are big M, big R. The initial velocity is angular velocity is v0, and of course the initial linear velocity is also v0. What we're asked to find is the tension in the rope and the acceleration of the center of mass of the yo-yo as it falls. Solution, we're going to need the summation of the forces equals mass times acceleration. And we're going to have a coordinate system that sort of slides down with this. So we're going to have to use, again, the summation of the torques about the center of mass is equal to I about the center of mass times alpha about the center of mass, like that. We are assuming it's unwinding without slipping, that sort of thing. So we might need to use V equals R omega or A equals R times alpha or something like that. But first off, let's draw, using this free body diagram, let's figure out exactly what the summation of forces in the y direction is equal to, and then let's figure out what the summation of the torques around the center of mass is equal to. So I'm going to start off with the summation of the forces in the y direction equals mass times acceleration in the y direction. I'm not going to subscript that y. I'll subscript that y here just because it's the statement. But in reality, it's the only acceleration we're dealing with. So I'm just going to call it A from there on out. The forces I have acting are, of course, the tension, which is acting in the upward direction, and the acceleration. Actually, I think I'm going to do this. I've got these drawn exactly backwards in terms of normally I use green for the positive direction and red for the negative direction. I really want to make since the acceleration is going down, I think it's better for us to use that as the positive direction. So ignore the negative sign, or excuse me, ignore the colors of these vectors. And what I'm going to do is say that my y-axis is pointing downward, in which case I'm going to get mg minus t is equal to ma. That's going to be equation one. And now I'm going to use the summation of the torques about the center of mass is equal to I times alpha. So the summation of the torques about the center of mass is equal to I about the center of mass times the alpha about the center of mass. I should point out that for a hoop like this, or for a disc like this, which is what a yo-yo is, either a disc or a cylinder, whether it's infinitely thin or really thick, it's still 1/2 mr squared. So I is equal to 1/2 m r squared is what we're using there. In this case, we have the weight mg is actually acting at the center of mass. So the lever arm for it is 0. That means there's no torque as a result of the mg, but there's definitely a torque as a result of the tension. So that tension, of course, once you draw the lever arm, you can see that the lever arm is in fact perpendicular to the force. So all I have to do is multiply the radius times the torque, and that will give me the actual torque. So I'm going to say T times R is equal to 1/2 mr squared times alpha cm. That's going to be equation two. Okay. Now, what I'm going to do is I'll solve equation one for t and plug that in two. So solve one for t and plug into two. So solving one for t is going to give me t is equal to mg minus ma, which is of course equal to m times g minus a. We could write it that way. I'm not sure which one's going to be better. I'm trying to solve it a different way this time than I did before, but that's okay. Now I've got that new equation 1 prime that represents t, and now I'm going to plug that into equation 2. So 2 and 1 prime give me the following. The t is going to be mg minus ma times r is equal to 1/2 mr squared, like that. And then that is multiplied, of course, times a center of mass. Now I've got an A and an alpha, or excuse me, alpha center of mass, and I've got an A and an alpha in here, and that compels me to use the fact that it rolls without slipping. So rolling, or I should say just without slipping, that tells us that A is equal to R times alpha center of mass. So I'm going to plug that in. Let's call this equation 3. Plug 3 into, I'm going to call this equation 4. So I'm going to plug 3 into 4. Now I'm going to get mgr minus mar is equal to 1/2 mr squared. But now I'm going to replace alpha with a over r. So that's going to be a over r, like that. Now I can see that this r is going to cancel out that exponent, leaving a 1 up there. And then this r and this r and this r is all going to cancel out. So now I've got mg minus ma is equal to 1/2 m times a. I can get the MA on the other side, and that gives me MG is equal to, when the MA comes to the other side, it's going to be positive. So 1 plus 1/2 is 3 halves. So that's going to make 3 halves MA. The M's now obviously cancel out, and that gives me that A is actually equal to 2/3 G. So that's the acceleration of the center of mass that we've been talking about, and that's what they wanted us to find. So now I've got the acceleration of the center of mass. If I wanted the actual angular acceleration, the alpha, then the alpha, which they didn't ask us for, is just given by A over R. So that would be 2G over 3R would be the alpha. But again, they didn't ask for that. Now I got to figure out what the tension is. And we already solved for the tension in equation 1 prime. So now I'm going to say from 1 prime, I get the following. T is equal to mg minus ma. That's equal to mg minus m times 2/3 g. Now, what I have is 3/3 minus 2/3 is 1/3. So this is going to give me 1/3 mg, and therefore the tension T is 1/3 mg. And that makes a little bit of sense because basically 1/3 mg means it's supporting 1/3 of the weight, and therefore it should actually accelerate at 2/3 of the normal acceleration that you'd expect. So that's why we got the acceleration is 2/3 and the tension is 1/3. Any questions on that, Nathan? All right, your book does example 1021, which I think is really neat to do, but it's a little more advanced than I would normally have my students do on a test or anything like that. But it's certainly reasonable, like if I gave you that for a homework assignment. So I'm just going to skip that and leave that for you guys to study. The same thing with example 1022. I think that's really good for you to understand. Like people don't really understand, like when you accelerate your car, uh, often when you hit the accelerator, the back end of the car steps down and the front end rises up, stuff like that. You don't necessarily get an understanding of why that's the case until you start looking at examples like 1022. What I'm going to do instead is just give you a brief intro to chapter 11 and just let you go. Specifically, chapter 11 is called Angular Momentum and General Rotation. And it specifically starts off with a ice skater doing the classic spinning thing. In fact, in this case, I think she might be doing like a double axle or triple axle or something like that, where she's in the actual air. Where normally you can just see it from when an ice skater has her arms completely extended like this and she's spinning kind of slowly. But as she brings her hands up like this, she's taking these big chunks of mass here and moving them to a smaller radius. And the moment of inertia is m times the radius squared. So that big significant change in r means the moment of inertia is going to get smaller. Since the moment of inertia gets smaller, that can actually allow the conservation of momentum, linear or angular momentum in this case, to kick in, and that's going to cause her to speed up. So I would like you to understand how that comes to be, and that's why I took the time to write these notes. So generally, we call the angular momentum L. That's the symbol we use, as you can see right here. We have the angular momentum is L. And if you're talking about a single body rotating with some angular speed omega, then the angular momentum is just the moment of inertia. Oops. It's just the moment of inertia times the angular speed. And it's given by that right hand rule, you know. So if it's rotating the direction of your right fingers, then your thumb is then pointing in the direction of the vector that represents omega. Now, if you figure out that angular momentum is conserved, then that tells you I omega in one case has got to equal I omega in the other case. And that's what I'm showing you right here is I omega equals I omega. When she is spinning, when the ice skater's spinning with her arms out, that means her body has the same moment of inertia, like her torso, her legs, her head, all of that has the same moment of inertia, whether she's spinning with her arms out or spinning with her arms in. Maybe a little bit of difference because the bones are moving a little bit, but not a significant amount. But when she pulls them in, then her arms gotten reduce her moment of inertia. So in going from her arms out to her arms in, the moment of inertia goes from big I to small I. But I times omega, whatever that is, has to be a constant. So we might imagine maybe I was 100 before and omega was 5 before. But now all of a sudden, and this is a vast overestimate here, now let's pretend her moment of inertia dropped down to 5. Well, the product of I times omega still has to be 500. So that means the omega has to be 100. So that's really what's going on with the ice skater as she spins. When her arms are out, she's got a big moment of inertia and a small angular velocity. But when her arms are in, she's got a small moment of inertia and a big angular velocity. And that explains it. This is conservation of angular momentum. But you might ask, well, how do we know angular momentum is conserved? And specifically, that's a question that you're supposed to know with linear momentum already. We discovered that from Newton's second law, F equals ma. That's not exactly the Newton's second law that Newton gave us. The Newton's second law that Newton gave us was F, the net force, is equal to dp dt, where p is the linear momentum, mass times velocity. So that's what I'm showing here is F equals dp dt. If, however, the net external force acting on the system is zero, then this being zero means this has to be zero. So I get dp over dt is equal to zero. And the only way a derivative is equal to zero is if that momentum, the quantity that's being differentiated with respect to time, must be a constant in time. So that is where we get conservation of linear momentum. P is equal to a constant because the net external force is zero. Well, guess what? The Newton's second law in rotational motion, as the way that Newton might have given us, is the summation of the torques is equal to dl dt, where L is the angular momentum. Okay. Now, again, if the summation of the torques is equal to zero, then this side is zero, and that means this side is zero. So dl dt is equal to zero, and the only way the angular momentum vector could be equal to zero, the derivative of it be equal to zero, is if the angular momentum vector is a constant, and that's what we say here. The L is equal to a constant. That is the very definition of conservation of angular momentum. All right, I think that's enough. This is a lot of material to cover in one session, anyways, and we could go a little further in chapter 11, but I think this is a good start. I can just jump in and solve examples next time. So you're free to go. I'll wait for the last person to leave in case anybody has any questions, but that's just you, Nathan. So can I ask you anything? Do you have any questions? Can I answer anything for you? I'm checking the chat. Ah, thanks for that. I just see, Nathan, I didn't have my chat box out, and I see that you caught me when I accidentally divided 0.385 by 0.5517. Uh, you actually caught it because you said, is it the division of 3.85 by 0.5517? Thanks for catching me on that. I'm sorry I didn't have the chat window open. I thought I did, but I just found it a second ago. So it does look like you're okay with the questions and all that stuff that I had, that you don't have any questions. So I'm going to go ahead and call it a day. And thank you for coming, Nathan. I appreciate it. And don't forget to get your tests done and your online test done. You actually have until Sunday night at 11:59 p.m. to do it. It should go up. I haven't had any requests to do it yet, but it should go up either tonight or first thing in the morning. Uh, but I've also took the time yesterday. Hopefully you got those text messages or those emails. I did replace all the test banks for this practice test, so you shouldn't have any more problems with the diagrams and photos loading. So if you do have any problems, or if you don't, for that matter, go ahead and let me know. But specifically, if you do have problems, let me know because I've got to figure out what's going on with that. Canvas is working on it. Our IT slash TCC's IT slash Canvas department is working on it as well, and I've been working on it, but I think we've got it nicked now. So hopefully that's the case. Have a good one and have a nice weekend, and I will see you next week. He was here. All right. So I'm going to stop sharing and thanks for coming, everyone. Have a good day. Bye bye.